Ever wondered how a simple chart can reveal the secrets of the universe? Let's dive into the periodic table. Hey, it's Leah, feeling energized and ready to explore something fascinating today.
And I'm Garrett, super intrigued by today's topic. Welcome to Laid Back Learning with Leah and Garrett. Today, we're delving into the world of the periodic table.
I still remember my first chemistry class. I was staring at this rainbow grid on the wall and it felt like a seating chart for atoms. Then my teacher said, "This is more like a map than a poster." That clicked for me. It wasn't just memorizing symbols, it was like learning the neighborhoods of a city, noble gases in one calm cul-de-sac, alkali metals in the lively downtown. I got hooked on how placement predicts personality. So big picture. The periodic table is an ordered arrangement of the chemical elements into rows called periods and columns called groups. Each element is placed by its atomic number, which is the number of protons in its nucleus. That number defines the element's identity. Same protons means same element, even if the neutrons vary as different isotopes.
Right. And the whole engine behind the table is the periodic law. When you line elements up by increasing atomic number, their chemical and physical properties repeat or recur at intervals. Why? Because their outer electrons settle into patterns called electron configurations. Electrons fill regions called orbitals in shells and subshells. Picture shelves with cubbies. The kind of cubby an electron goes into, S, P, D, or F, shapes the element's behavior. As those outer patterns repeat, the properties repeat. That's pretty cool, right?
And we have to give a huge nod to Dmitri Mendeleev, a Russian chemist in 1869. He arranged elements by mass back then and noticed repeating patterns, leaving blank spots for what he called Eka elements. He even predicted their properties. Later, scientists discovered atomic number, the true ordering key, and quantum mechanics explained why the repeats happen. That fixed some mass-based mix-ups and made the map rock solid.
You'll hear people talk about blocks on the table. S, P, D, and F. That just means which subshell the valence or outer electrons are filling as you move across. S holds 2 columns, P holds 6, D holds 10, and F holds 14. The order they fill mostly follows something called the Madelung rule. It says orbitals fill in order of increasing n plus L, which is a quick way to rank their energies. If that sounded crunchy, here's the simple version. Lower energy spots fill first, with a regular pattern that sets the table's shape.
And because only those outer electrons usually join in bonding, elements in the same group share a vibe. Oxygen, sulfur, and selenium, for example, each have 4 electrons in that outer p set, so their chemistry rhymes. Minor quirks exist. Chromium and copper like to tweak their electron counts in the gas phase, but in real materials, bonding evens things out, so the group trends still guide you.
And just to clear up a common question, isotopes. Same element, different neutron counts, different mass. The table doesn't split them into separate boxes, it lists one box per element. The number you often see under the symbol is a weighted average mass, the standard atomic weight, based on how common the isotopes are in nature. If an element doesn't have a stable natural mix, you'll often see a mass in parentheses, which usually points to the most stable isotope instead of an average.
All right, story time in a bit more detail. In 1869, Mendeleev drew up his table by atomic mass and boldly left gaps, predicting the sizes, densities, and reactivities of elements not yet found. That confidence came from the repeating patterns he saw, even without knowing atomic number.
By the late 1800s, chemists were catching on that this periodic law thing was legit. It wasn't a cute chart anymore. It became the search engine for new elements, pointing where to look and what to expect.
In the early 1900s, there was a big pivot. Scientists tied element identity to atomic number, not mass, that's the proton count, and suddenly weird exceptions vanished. Quantum mechanics arrived, with orbitals and shells explaining why the periodic law works at all.
In 1937, technetium, element 43, became the first element discovered by synthesis in a lab. It had been a glaring blank spot, making it confirmed Mendeleev's map had been pointing to a real place on the chart.
And then 1940 brought neptunium, Element 93, the first transuranium element, meaning beyond uranium. That kicked off a wave of new, artificial elements you can't scoop out of the ground because they decay too fast.
Quick shout to some rules of the road. Wolfgang Pauli gave us the exclusion principle. Two electrons can't sit in the exact same quantum state. Friedrich Hund added that electrons spread out in equal energy orbitals with matching spin before pairing. Together, they explain the stacking pattern of electrons that drives the table's layout.
As shells and subshells fill in that pattern, you even get a signature rhythm to the period lengths, 2, 8, 18, 18, 32, 32. Each time a new type of orbital joins the party, the row gets longer.
One more cool twist from back then. Some elements were actually made in labs before anyone found them naturally. Besides technetium, promethium, astatine, neptunium, and plutonium showed up in particle accelerators and reactors first, then were identified in trace amounts in nature later.
Moving into the middle of the story, in 1945, Glenn T. Seaborg, an American chemist, realized the actinides form an F-block series like the lanthanides. That was huge. It reshaped the modern long-form table and explained the chemistry of those heavy elements much better.
That's why you often see the F-block detached under the main grid. It's an editorial cutout to save space. In a true 32-column longform, those rows dock right into period 6 and 7. Same sequence, just wider paper.
And the labeling of groups got a cleanup too. For a long time, people used Roman numerals and A or B letters, which changed from book to book. In 1988, IUPAC, the International Union of Pure and Applied Chemistry, standardized the groups to numbers 1 through 18. Much less confusion.
Here's a wild stability fact. Bismuth was long thought stable. It turns out its most common isotope is actually radioactive with a half-life around 2 times 10 to the 19th years. That's about 1 billion times the age of the universe. So for all practical purposes, it just sits there. But technically, it does decay.
Speaking of extremes, no element heavier than Einsteinium, element 99, has ever been seen in a visible macroscopic chunk in pure form. Even astatine has never been seen that way, too radioactive, too fleeting. Francium has only been photographed by the light it emits from tiny amounts. It vanishes before you could ever scoop it up.
And in the super heavy corner, elements 109 through 118 are so short-lived that we don't even have experimental electron configurations for them. We lean on calculations to predict where their electrons go. Their boxes sit in the right places, but the details are still a work in progress.
Now the final lap of the timeline. In 2002, scientists synthesized oganesson, element 118. In 2009, tennessine, element 117, was made. By 2010, every element from 1 to 118 had been created or identified, completing 7 full periods.
And in 2016, the last of those new elements received official names. That was the moment the 7th row's roster was fully christened, so to speak.
A more recent update in 2021, IUPAC issued a report backing the idea that in Group 3, the lineup should be scandium, yttrium, lutetium, and lawrencium. The argument leans on how the F-shell closes and which orbitals act as valence. It's tidy electronically and chemically, even though older charts sometimes still show lanthanum and actinium there.
And not every debate is settled. Hydrogen's and helium's exact spots still spark discussion because they straddle different ways of deciding. Do you prioritize electron count or real-world behavior? That kind of nuance is part of what keeps the table alive as a teaching tool.
Looking ahead, some theorists think elements beyond 118 might not follow today's patterns cleanly. Relativistic effects, basically electrons moving so fast that Einstein's physics tweaks their energies, could remix the order. So the map may need extensions or new legends one day.
Okay, let's put a friendly spotlight on a classic controversy. Hydrogen and helium. Where should they live on the table? Group 1 is the alkali metals, like lithium and sodium. Group 17 is the halogens, like chlorine and fluorine. Group 18 is the noble gases, like neon and argon. Group 2 is the alkaline earth metals, like magnesium and calcium.
I'm going to plant a flag. Hydrogen fits Group 1 best. It has a single electron in the 1s orbital. That's the s block. It often loses that electron to form H+, the hydrogen ion, just like alkali metals lose one electron to make +1 ions. If we're organizing by electron configuration and the simplest bonding behavior, group 1 makes sense.
I hear you, and I'm kind of split. Hydrogen also acts like a halogen sometimes. It can gain an electron to become hydride, H-, which echoes how chlorine gains an electron to make chloride. And hydrogen is a diatomic gas at room conditions, H2, which vibes more with halogens than with shiny, soft metals. So I could get behind a dual placement or even floating it above the table to signal it's special.
Why would we float it, though? Doesn't that make it harder to teach the idea that the table predicts behavior?
Fair question. I think the case for floating is to warn students that hydrogen is a boundary case. It follows the same S1 electron count as group 1, but its chemistry splits the difference because it's so small and has no inner electrons to shield the nucleus. In other words, its first shell is unique enough that the normal rules stretch a bit.
All right, helium next. I'm team group 18. It's famously inert at standard conditions, meaning it barely reacts at all. Its 1s2 outer shell is full, and in practice it behaves like a noble gas. IUPAC even rejected moving it to group 2 back in 1988. Keeping it with the noble gases reflects how it acts in the real world.
I'm mostly with you, but I'll play devil's advocate. Helium is an S-block element, not P6 like neon and argon. In the solid phase, at very low temperatures, helium crystallizes in a hexagonal close-packed structure, which is what group 2 metals like beryllium and magnesium do. So some chemists say maybe helium should sit over group 2 to highlight those electronic and structural parallels. It's a minority view, but it points out the tension between configuration labels and chemical behavior.
Why would the missing p electrons matter if helium stays so inert either way?
Because p orbitals change how atoms polarize and bond. A full p shell, P6, gives a kind of second layer of stability that the noble gases share. Helium lacks that, yet it's still super inert because its 1s shell is tiny and tightly bound. So the argument is the reason helium is inert is different from neon's reason. Group 18 bundles them together by outcome, not mechanism. But yeah, in everyday chemistry, they both just chill.
I can live with that nuance. Maybe the map can show behavior first and add a footnote about the mechanism. For learners, helium with the noble gases tells the most useful story.
Same with hydrogen. Put it over group 1 to start, then mention it, sometimes cosplays as a halogen. That's something to chew on, huh?
Culturally, the periodic table is an icon. It's on classroom walls, lab doors, t-shirts, and posters. Designers use it in science-themed art because it's instantly recognizable, a grid of knowledge, a blueprint for matter. It's wild how a chart from the 1800s became a visual language everyone knows.
And the color-coded versions pack so much in. Metals here, non-metals there, blocks by shade, state of matter by border. It's a compact infographic before infographics were even a thing.
Let's play a what if. What if atomic number had been discovered before Mendeleev drew his table? If he'd arranged by proton count from day one, a lot of the early misplacements by mass would never have happened, and the periodic law might have landed with fewer skeptics because the anomalies would be gone from the start.
Totally. And maybe the momentum to find missing elements would have been even stronger, since the gaps and their order would be super crisp. But here's a twist. Would Seaborg's 1945 actinide insight have been delayed? I think probably not. The actinide's chemistry still screams F-block, which only becomes obvious when you actually make and study them. That was more about new elements than about the numbering system.
Right. The experimental chemistry had to catch up. Maybe atomic number first would have changed the teaching path. Less confusion over group labels, less back and forth about mass anomalies. But the deeper relayout of the bottom of the table still needed the actinides to be born in the lab.
And I wonder if a cleaner early table would have made the hydrogen and helium debates louder sooner. If everything else lined up perfectly, those two exceptions would stand out like neon signs. Maybe we'd all have grown up seeing hydrogen floated and a little note under helium saying S2 behaves noble.
Either way, the heart of it holds. Arrange by atomic number, let electron configurations explain the rhythm, use groups to predict behavior, and keep room for edge cases and future discoveries.
Stay curious, everyone. Until next time.
And keep exploring the world around you. Bye for now.